ఈ ఫ్యాన్ ఆఫ్ చేస్తాను. Yeah. Good afternoon to all. Yeah, welcome to afternoon session. So, in afternoon session, we'll try to discuss advanced speed control of three-phase induction motor using field orientation method and director control. These two methods we'll try to complete, right? Why? Because these two methods are very popular, particularly in EV application, electric traction application, right? Even in Vijayawada steel plants, they are adopting these methods to control the electric drives instantaneously, right? So here what we discussed before break, we discussed about Clark transformation, Park transformation, next cross transformation. See, even if you take cross transformation, Park transformation or cross transformation, only thing is reference point is changing, but actual system response is same. Even if you take number of variables 3 or number of variables 2 with sinusoidal in nature or number of variables 2 in DC nature, all will give same information with less complexity. That's why here nowadays all grid connected inverters in power quality issues, in electrical drives, right, in PV application, see, all everyone they are adopting transformation technique to control the signals effectively. Now come to hierarchy. This is a very important concept, right? Why? Because this block diagram is common for all electrical drives. Even see, low power drives, high power drives, DC motor, DC drives or AC drives, this control hierarchy is common. Control sequence, right? Now, what is the base for this sequence? Before going to discuss advanced speed control methods, in all advanced speed control methods, they are following this structure. Why? Because here we don't have any freedom to develop the control hierarchy in electrical drive. What is the base for developing control hierarchy scheme? How they will develop scheme? See, observe this block diagram carefully. There are two paths are there. See, this is one path, right? This is one path, another path. There are two paths are there. There are two control signals are there. There are two paths are there for control the two variables, right? This block diagram, please try to understand, this block diagram is common for all electrical drives. This is what they are adopting in robotic application, aerospace application and submarine application. Now question is, why they are keeping torque controller closely to power electronic module? After that, why they are keeping speed controller? Why they are giving least priority for position controller? Anyone, what is the base for selecting the position of the controller? How many controllers are there here? How many controllers are there? Position controller, speed controller, torque controller, this is flux controller. There are 4 controllers are there. But thing is, here this flux controller is independent of the torque controller. This is the path. The main object of this path is control the torque. The main object of this path is control the flux. Now question is, why we need to control the flux and torque? Any motor, whether it is a DC motor or AC motor, with respect to control point of view, target variables are only 2 for electrical drives. One is torque, another one is flux. Now question is, why we need to control the torque and flux? Anyone? You got my point? Any electrical drive, whether it is a DC drive or AC drive, single phase or multi phase or induction motor, PMSM machine, or BLDC motor, or switch reluctance motor. If you take any electrical motor, see, whenever you want to control the motor, you have to design the controller, right, in two different logic. One is for torque controller, right, another one is for flux controller. So torque and flux, these two are main target variables in case of electrical drive. These two are called control objectives, right? Now question is, why we need to control the torque and flux? Anyone? Aim is speed control. If you want control the speed of the shaft, or if you want control the position of the shaft, necessary thing is you need to control the torque. Torque is the main cost component to control the speed. Clear? Understood? Speed is the main component to control the position. If you want change the position, you have to rotate the rotor. If you want to rotate the rotor, it requires force. There is a cause and effect is there. See, there is any torque is there in machine, what it will do? Immediately it will drive the shaft. You will get motion. Because of motion, what will happen next? Position of the shaft will vary. Theta of the shaft will vary. Understood? So if you want to change the theta, you need to change the speed. If you want to change the speed, you need to control the torque. Clear? Torque is the main cost component to change the speed or position of the shaft. Understood? In case of electrical circuit, if you want to change the current, you need to regulate the voltage. You don't have any option. Voltage is the main cost component to control the current in case of electrical circuit. In case of mechanical system, if you want to change the position of the shaft or if you want to control the speed of the shaft, only option is you need to control the torque. That's why your target variable is torque. The main object of this path is torque controller. The main object of this path is flux controller. Now question is, okay, torque is main responsible for changing the speed or changing the position. Why we need to take one more path for controlling the flux? That is my question. Why we need to take, please try to understand, this is the standard block diagram common for all electrical systems, high performance application, robotic application, aerospace application, particularly in robotic application, here position is so important. Even in control system also, control system application, position is so important, right? See, wherever position control requirement is there, they will start the reference here. Particularly in electric drives application, speed is the main requirement. So, reference signal is starting from here. In robotic application, your reference point will start from the theta star. Application to application, reference will change. In electric vehicle application, main requirement is with respect to customer point of view, requirement is speed. In robotic application, main requirement is position. 90 degrees, 40 degrees, 10 degrees, 5 degrees movement. Right? Discrete movement is required. Based on application to application, it is different. See, even if you want to change the position or speed, only option is you need to regulate the torque. That is fine. Torque is the main cost component to change the speed or position of the shaft. Now my question is, why we need to take another path for flux controller? Why we need to target torque? Why we need to target flux also? By using flux controller, what we are doing? In case of armature control method, what we are doing? We are maintaining magnetizing flux constant, field flux constant. After maintaining field flux constant, what is the advantage? See, IF is constant, what is the advantage? Nonlinear equation is converted to linear. To decrease the number of variables involved in the torque expression, they are taking one more path for maintaining magnetizing flux constant. The main object of this path is it will maintain air gap flux is constant. Whenever you want to control the speed below base speed. If you want to control the speed above base speed, flux weakening zone, here this path will take care based on the required speed. So finally, in case of electrical drive, any drive, target variables are only torque and flux. Torque is the main cost component. According to Lenz's law, they will decide Now question is why they are keeping torque controller here? Why they are keeping speed controller here? Why they are keeping position controller here? That is my question. Anyone? What is the base for deciding the position of the controller? You have studied control system subject. Third year students, you have studied control system. You heard about PA controller, PID controller or P controller or I controller, integral controller. See, if you take any controller, P controller or I controller or PID controller, input to the controller is always error. Am I correct or not? Input is error. What is the output of the controller? It is a cause component. Output of any controller will decide the magnitude of the main cause component. See? Okay. Here this is reference here, this is actual signal. What you will get here, you will get error. This is about controller. See, controller output, many of the students they don't know what is the expected output of the controller. If you want to identify what is the output of the controller, first step is you should know what is the cause and effect relationship for a particular system. In case of armature circuit, if you take armature circuit, in case of armature circuit, what we are doing, we are applying VA, we are regulating VA so that we can control the error, right? See, in case of DC motor, after adopting armature control method, what we are doing, we are adjusting the VA and VF we are maintaining constant. So, VA is the main responsible component for rectifying the current error. So, let us assume that here our requirement is IA star. Actual current is not matching with, if actual current is not matching with reference, then here you will get current error, IA error. If input is current to the controller, input is the current signal. Am I correct or not? If input to the controller is current, please try to understand, then output is always voltage. What is the reason? This is based on Newton's law. See, what is the purpose of controller? To rectify the error, to minimize the error, to make error forcefully zero. In order to bring the error zero, only option is you need to identify what is the main cause component to control IA. Our aim is controlling the IA. Our aim is bringing the current, actual current. Our aim is matching the actual current to the reference. If reference and actual both are matching, error will zero. But problem is, this error we can control only by adjusting the VA. That's why the expected output of the controller is voltage. Voltage is the output. So your controller practically, please try to understand, see, this is called current controller. We are trying to rectify the current error. If there is any current error is there, the expected output of the current controller is voltage signal. There is no option. Please try to understand. Why? Because voltage is called potential element, current is called kinetic element. Current we can modulate, current we can modify by using voltage signal. Understood? Now come to, this is called current error, current controller. Now come to, let us assume that omega m star, speed controller. This is called speed controller. This is actual speed, then this is speed error, omega m error. So what is the expected output of the speed controller? If there is any speed controller is there in your loop, speed controller nothing but input to the controller is speed error. What is the expected output of the speed controller? What is the main cause component? Please try to understand. Your job is you need to identify what is the main cause component to rectify this error. Who will take responsibility to minimize this error? Speed, how we can make it 0? How we can control? Torque. So the expected output of the speed controller is torque. Or torque or current, both are same. Torque is directly proportional to Ia, right? So if there is any speed controller is there, the expected output of the speed controller is always current or torque. Clear? Now come to last one, position, theta. How we can, theta error, if there is any theta, if there is any error is there, how we can minimize the error? How we can minimize the error? Who will take responsibility? How we can change this position? By rotating. Speed is the main cause component. Speed omega m will decided by the angle or position controller. So finally there are three controllers are there in electrical drives application. There are three controllers are required. One is for torque controller, another one is for speed controller, another one is for position controller. But problem is here, see, if you take position controller, the expected output from the position controller is reference speed. This reference speed is coming, right? This reference signal, how much, what is the reference value of the operating speed will be decided by the position controller. Speed controller will decide what is the reference current you need to maintain. Clear? There is a link is there. Interlink is there. Now question is, see there are three controllers are there. Inherently there is a interconnection is there. So what, see out of these three controller, which controller you have to give top priority? Which controller should work very fast? Which controller's bandwidth should be more? Torque controller. Example, best example I will take college. In this college, this is a system, right? See students are nothing but torque controller. If students are working effectively, who will get good name? Faculty will get good name. If faculty is getting good name, department head will get good name. If department head is getting good name, automatically your principal will get name. If principal is getting name, automatically college name will improve. Understood? But thing is, in order to get good name for the college, who has to work really? Student has to work, not faculty. Student bandwidth should be very, very high. If students are working effectively, right? Inner loop, where torque is nothing but inner loop. It is there inside the controller. Outside, position controller is there. After that, speed controller is there. After that, torque controller is there. But thing is, in order to rectify the position error or speed error, your torque controller should work effectively. First thing is, first torque controller should act first. After that, if torque controller is working effectively, immediately what will happen? Your actual current will come to, it will match with reference current. Once reference current is matching with the actual current, then speed error will come to 0. Once speed error is coming 0, nothing but indirectly we can conclude that actual speed and reference speed both are matching. If actual speed and reference speed both are matching to each other, then you can expect that theta error will come to 0. Next sample. Clear? This is called hierarchy, control hierarchy. First torque controller should work effectively. After that, speed error will come to 0. If speed error is 0, automatically position error will come to 0. That's why here the bandwidth of the inner loop should be very, very high compared to outer loop bandwidth. If students are working fine, this controller is working fine, automatically next step your speed error will come to 0. If speed error is 0, in next sample period, next instant your position error will come to 0. This is the sequence. We don't have any option on this one. Why? Because here there is a cause and effect is there. Position we cannot change simply like that. If you want to change the position, first you have to regulate the speed. If you want to regulate the speed, next step is you need to regulate the torque. If you want to regulate the torque, you need to control the current. If you want to control the current, you need to regulate the voltage. This voltage This voltage you cannot modify simply like that. This voltage through power electronic module we have to regulate. This is the heart of the controller, power electronic module. Understood? So finally, this logic or everything will decide what is the duty period of the each switch. Your control logic will decide. Based on the duty period, energy will transfer from source to machine. Energy will transfer effectively. If energy is transferring effectively, automatically system characteristics will change based on the requirement. You got my point? So finally what we are doing, we are trying to modify the torque speed characteristics of the motor based on the requirement. Here inherently motor characteristic, it is coming under your control. This one, this is under your control. This is the actual system, this is the control system, this is the control mechanism, this is about power semiconductor element. By taking combination of power semiconductor element and control logic, we can change the motor characteristics based on the load requirement. Based on the load requirement, we can change effectively. So that's why here this is called universal block diagram. This block diagram is common for all electrical drives. Robotic application, satellite application, electric vehicle application, right? Now we will try to discuss principle of the field orientation method. How we are going to control the induction motor similar to DC motor. We will try to discuss. In field orientation method, first what they will do is, this is the problem already we discussed. Before lunch break, what is the problem with induction motor? What is the problem with induction motor? Whatever current is flowing to the stator side, that current having two components. Inherently there are two components are there. One is flux producing component, another one is torque producing. But in case of DC machine, there is a different path is there for field current and armature current. Independent control is possible, but here independent control is not possible. That's why what they are doing is, they are by adopting transformation techniques, first they will transfer these two signals with 90-degree displacement. So this is about transformation technique. So this is about resultant stator current, this is about resultant rotor flux. See, this is about after transformation. See, before transformation, what is the order of torque expression? Before transformation, morning we discussed for three-phase induction motor, we got, see, finally we conclude that order of the three-phase induction motor is 7th order. After converting three-phase variable to two-phase variables, what is the order? 4. Finally, 4 variables are there. Still it is in nonlinear. Understood? Still it is in nonlinear. One more advantage of this equation is there is no theta. There is no delta here. Is there any delta here? That is the beauty of transformation. Anyway, it is fine. Good thing is there is no nonlinear component. There is no sign component here. One more advantage is number of variables are changing from 7 to 4. But thing is, what is our requirement? Torque should be linear. Still it is a non-linear, 4th order, but we require 1st order to control the torque instantaneously. Torque equation should be 1st order. So how they will convert? See, morning already we discussed resultant stator flux or resultant rotor flux we can produce using three-phase currents. IAS, IBS, ICS, resultant is IS. Lambda or resultant rotor flux we can produce using resultant A phase, B phase, C phase rotor flux. By using A phase, B phase, C phase rotor flux, we can resolve the resultant rotor flux. Without taking three-phase variables, by taking two-phase variables also, we can produce same element. Same information we can produce. So here, IDS and IQS, these two components will take responsibility to produce the same effect of the three-phase variables. Here also lambda dr and lambda qr will produce the same effect of the three-phase system. Whatever information is there with three-phase variables, same information, same characteristics you will get with less number of variables after adopting transformation methods. But here problem is still your torque is in higher order, still it is in nonlinear mode, it is unwanted. So how we can convert from fourth order to second order to first order. Aim is first order. If torque profile of the induction motor is order of the torque expression is 1, then the performance of the induction motor, the performance of the B student is exactly similar to performance of the A student only. That is what we discussed morning session. Anyone, please tell me, identify. This is the phasor diagram after changing the variables, 3-phase variables to 2-phase. Anyone, how we can minimize the variables? Observe this equation. Observe this equation. If you are able to maintain this component 0, how we can maintain this component 0? This is very important. If it is a 0, then automatically what will happen? If it is a 0, then order of this equation become second order. Now question is, in case of field orientation method, big challenging is making lambda QR, Q axis component making 0. That is a big challenging in field orientation method. How they will maintain lambda QR? See the phasor diagram. How we can make lambda QR 0? See, morning we discuss. What we discuss morning? If reference person is sitting on the same frame of the A person, what is the speed? 0. If both are in phase, here with respect to other person also, relative motion between these two is 0. Nothing but it is looking like DC. That is what we discussed before lunch break. See here, problem is there is a delay is there. There is a space delay is there between lambda dr and lambda r. Lambda r is the resultant rotor flux. Lambda dr is the d axis. After transferring the signals from 3-phase to 2-phase, lambda dr is the real component. This is imaginary component. Our aim is lambda QR should be 0. If you want to make lambda QR 0, this one, d axis is nothing but reference axis. This reference axis you have to bring in phase with actual flux position. If d axis is coming exactly in phase with lambda r, how you will get lambda r position? Practically, there are position sensors are there, flux sensors are available. Otherwise, there are mathematic techniques also there, right? By using estimation methods or by using flux sensors, right? Or by using encoders, we can get information about rotor flux position. If it is a BLDC motor or if it is a permanent magnet synchronous motor, rotor position and rotor flux position both are same. Please try to understand. If it is a synchronous machines, rotor flux position and rotor position both are in phase to each other. By using incremental encoder, we can get the information about rotor position. Once you know the rotor position, once you know this angle, if D axis also maintain with same angle, once D axis is coming in phase with lambda r, automatically if D axis is coming in phase with lambda r, what is the effect of imaginary component? Very simple. If D is coming in phase with actual vector, effect of imaginary component is 0. How they will maintain? First step is, first they will sense the position of actual flux. So once you know the position of actual flux, with the same angle, if you rotate D axis, right, automatically lambda QR is 0. If lambda QR is 0, this is the phasor diagram. After, this is called orientation. Field orientation. That's why this method is called field orientation control. We are trying to change the reference person in phase with flux vector. We are aligning the reference person in phase with actual flux position. This is the main heart of the control logic. Please try to understand. If you are not aligning properly, then what will happen? We cannot eliminate the imaginary component. We cannot eliminate the lambda QR component. Right? If lambda QR effect is there, then torque we cannot control instantaneously. It will not come linear mode. It will not come to first order. This is very important. In case of field orientation method, big challenging is calculation of the rotor position, rotor flux position. In case of permanent magnet synchronous motor, brushless DC motor, it is not a problem. But in case of induction machine, it is a big challenging. Estimating the lambda R. There are a lot of research papers are there how to estimate the position of the actual rotor flux position. Right? Direct field orientation method, indirect field orientation method, right? There are so many methods, A methods. Nowadays, there are so many optimization methods also they are adopting to identify the rotor flux position with less number of parameter effect. Okay? So once D axis is coming in phase with lambda R, advantage is lambda QR effect is 0. If lambda QR is 0, so finally how many variables are there? 2. Still it is in nonlinear mode. Right? So next one more thing is by maintaining rotor flux as a constant, by maintaining this flux as a constant, if it is a constant, then what will happen? Your torque equation become 1. You can think this is the beauty of the controller. Finally, your 3-phase induction motor torque equation, it will come into first order after adopting transformation plus orientation control. Clear? Everyone understood? So by taking the transformation method, what will happen? 7th order to 4th order it will transfer. After after shifting the reference point in phase with rotor flux position, 4th order to 2nd order. After that, after adopting the flux control mechanism, by using flux control path, we can maintain magnetizing flux as a constant. If it is a constant, then torque is directly proportional to only IQS, Q axis component. This Q axis current we can control simply. One variable, if there is a one variable is there, we can easily control. If it is a, see finally, mentally what we are doing? Your 3-phase induction motor, basically it is in non-linear. Clear? But by using control mechanism, by taking the combination of power electronic module and control logic, we can able to transfer the characteristics from 7th order to 1st order. Nothing but, 1st order nothing but, we are meeting the benchmark. What is our benchmark? 1 DC motor. Whatever profile, whatever torque dynamics you are getting in DC motor, same dynamics you will get even if you take nonlinear system, even if you take higher order system also, by using power converters and power electronic module and control logic, we can able to change the characteristics. Mentally we can improve the profile. Clear? Everyone understood? This method is called field orientation method. This is a very powerful method. Most of the electric vehicle application, industrial application, in traction application in foreign countries, except in India, in foreign countries they are adopting this method for traction application also. But see, coming next 3 or 4 years, definitely in India also they are trying to replace DC series motors with induction motor with FOC method, field orientation method. The advantage of the field orientation method is torque profile is exactly similar to DC machine after orientation. Performance is same, maintenance is 0, lifetime is very good, heating effect is less, size is very compact, power density is more. There are a lot of advantages are there with respect to induction motor. Clear? That's why induction motor 80 to 90% electrical power, whatever power is generated by the generator stations in India or other countries also, 80% power consumed by the industrial drives only. All industrial drives are induction motors. Understood? So this is called advanced speed control methods for electric. This is why it is called advanced speed control method. We are getting, see, by controlling the position of the reference flux. So finally, by bringing the reference flux in reference flux in phase with actual flux, here your torque profile of the induction motor, it is changing from 7th order to 1st order. That is the advantage. Right? Anyone having doubt? This is about simulation. See, if I show the simulation, you will understand, you will get clarity. So this is about reference speed. right? So reference speed they will compare with actual speed. This speed will come from the encoder or tachometer. Practically, speed signal will come from the encoder only, sensor. Next, so here speed error they will send through the speed controller. What is the output of the speed controller? Reference torque. So reference torque they will compare with actual torque. Then if there is any torque error is there, your torque error will, so torque error nothing but current error is there, your torque controller will generate voltage signal. So finally what is the voltage signal here? What is the voltage signal? Sorry, what is the signal here? Voltage. Torque controller output is always voltage, speed controller output is always torque. Right? This is the main object of this path is, what is the object of this path? To control the torque. What is the object of this path? To control the flux. There are two paths are there. So finally, this is about transformation. This is about logic. Why this transformation is required? This is called, here please try to understand, if you want to implement FOC, it requires two transformations. One is called forward transformation, another one is called inverse transformation. What is meant by inverse? What is forward transformation? 3-phase to 2-phase is a forward transformation. Why we need inverse transformation? Why 2-phase to 3-phase we need to transfer? Our system is a 3-phase. Actual system is a practically it is in 3-phase system. Our natural system is in 3-phase reference frame. That's why here it required 3 modulating waveforms. Right? To generate the 3 modulating waveform, it required inverse transformation. This is about inverse transformation, 2-phase to 3-phase. Finally here 3-phase signals are coming. These 3-phase reference signals, if you compare with actual, then you will get error. This error if you send through the power electronic module, then power electronic module will, control logic will decide what is the duty period. Based on the duty period, your voltage source inverter will control the voltage and frequency. This is about induction motor. This is our actual system. So from the actual system we can get the information. Clear? This is simple MATLAB, MATLAB block diagram for the Simulink block diagram for the field orientation control of the 3-phase induction motor. Here what is the problem? Before going to discuss another advanced speed control method, I want to ask one important question. What is the problem here? What is the main drawback of the field orientation method? It required transformations. 3-phase to 2-phase is required. Orientation is also very big challenging. Field orientation is also very challenging. These two are very difficult, practical. Right? So in order to eliminate the transformations and in order to eliminate the orientation concept, here in 1980s they have proposed direct torque control method. In case of field orientation method, we are controlling the torque in terms of IQS. In terms of current, we are controlling the torque. Nothing but it is called current control mechanism. We are not controlling the torque directly. We are controlling the torque indirectly. Right? That's why field orientation method is called indirect torque control method. So in 1983, they have proposed advanced method, one more advanced speed control method for electric vehicle application, that is called direct torque control. In direct torque control method, see the main object of the direct torque control is without any transformation, without any orientation, torque and flux we can control effectively. That is the primary objective. So by using phasor diagram, I will try to explain this concept. This is about phasor diagram. Already you might studied in undergraduate course, right? This is standard phasor diagram. In case of induction motor, what is the nature of stator flux and rotor flux? Anyone? See, what is the mathematical expression for torque? Torque equal to xi s, xi r sine delta. That is what we discussed morning session. This is the stator flux. Stator flux. This is about rotor flux. This is about angle, space displacement angle. See, in case of induction motor, the nature of the rotor flux is here the speed of the stator flux and speed of the rotor flux both are rotating with same speed. Relative motion is 0. But rotor flux always lags the stator flux if it is operating in motoring mode. Please start understand. This is very, very important. If induction machine is operating in motoring mode, rotor flux always lags the stator flux. If machine is operating in generating mode, rotor flux will lead the stator flux. Clear? This is very important. In case of induction machine or synchronous machine, if machine is operating in motoring mode, your stator flux is dominating. Your stator flux leads the rotor flux. Otherwise, if it is operating in generating mode, your rotor flux leads the stator flux. Now my question is how we can control the torque and flux. Anyone? What is the name of this control logic? What is the name here? Full name is direct torque and direct flux method. Direct torque and direct, generally they will call DTC, direct torque control, but actual name is direct flux and direct torque control method. How we can control the torque and flux directly? If you want to control the system, already we discussed, first you should know what is the actual system characteristics. In case of induction motor, the nature of the torque is, it is a function of stator flux, rotor flux and angle. Right? Clear? Anyway, one more important thing is rotor flux we cannot access. In case of induction motor, particularly in case of squirrel cage induction motor, you don't have any access on the rotor current or rotor voltage. It is not in your control. Only stator terminals we can access. Through stator terminal we can control the voltage. We can access only stator terminals. We cannot access rotor bars. Right? See, in case of, it is a very simple, see, this is the standard equation, d is by dt equal to applied voltage minus drop. If you neglect this drop, d is by dt. Stator flux we can change by using Vs, by using voltage. Nothing but if there is any flux error is there, we can rectify by using voltage vector. In case of direct torque control method, you no need to take any help from the current. It is not a current control. It is a voltage control. It is a direct control of the flux and torque. Now my question is very simple. It is not a big task. Very simple thing is, right? This is the nature of the induction motor, right? So by using this nature of the induction motor, see, whatever nature is there, using that nature we can control the torque and flux effectively using single voltage vector. See, d is is by dt what it means? Anyone? What it will indicate? Delta is nothing but change in the stator flux equal to Vs into delta T. Vs is nothing but resultant voltage applied across the motor terminal. Delta T is nothing but sample period of the controller. It is a fixed, it is not a variable, delta T. Right? So, in a particular sample period, in a particular control period, by choosing proper voltage vector, by choosing this voltage vector, we can control this vector effectively. That is the simple principle. This is, if you understand this equation, here operating principle, control logic of the DTC, we can understand very simple. See, in case of induction motor, please start understand, you don't have any freedom on the rotor flux. But thing is, stator flux we can control effectively. Stator flux we can control through stator voltage, right? So this is the standard mathematical expression d psi s by dt equal to Vs, supply voltage, resultant voltage. So from this expression, the same expression, we can rewrite like this. We can rewrite like this. So what is the final conclusion is, from this expression, we can conclude that flux vector we can control effectively in a particular control period. This is nothing but control time. This is nothing but Ts, sample period, control period. Within this period, by choosing proper voltage vector, we can control the stator flux effectively. Now question is, by seeing this equation, many of the students, they are not understanding how we can control the flux. By controlling the flux, how we can able to control the torque. That question will arise, right? If you want to understand this one, first you should know the characteristics of the inverter. If you take voltage source inverter, here this is the nature of the voltage source inverter. V1, V2, V3, V4, V5, V6. See, please try to understand, for undergraduate students, it is very difficult to understand this concept. At least try to understand the fundamentals, it is fine. Later, see, I am telling third year students or second year students, very difficult to understand this concept. But at least try to understand the basics. Some key points are there. I will try to highlight important points, right? See, this is the phasor diagram of the resultant phasor diagram of the voltage source inverter. Power semiconductor device phasor diagram, voltage phasor diagram. Why? Because there are 6 switches are there in voltage source inverter. By using these 6 switches, we can able to produce 6 voltage vectors with a different phase shift. Magnitude is same, length of the vector is same. Only thing is position is different, right? Position is different. By selecting proper combination, we can get V1. We can produce V2 vector with 60 degrees, 120 degree, 180 degree, right? 180 plus 60. Like that, we can produce different voltage vectors, but amplitude is same. Vector length of this vector, all length is same, but position is different. This one, by changing this inverter switching states, we can produce. But once you pick the 3-phase voltage source inverter, the characteristics of the 3-phase source voltage source inverter will not change. This is the behavior. Please try to understand. This is the expected output of the voltage source inverter. Voltage source inverter output is only 6 active voltage vectors. Understood? 6 voltage vectors, voltage signals you will get. Right? Now, the same voltage vector I will impose on the flux. Why? Because voltage is the main responsible component to change the flux. Right? This vector I will take here. Then you will understand. Same phasor diagram. I will take V1, V2, V3, V4, V5, V6. This is about now see, it is a very beautiful concept, don't get confused. If you select V2, what will happen? This is the actual flux position. This is the position of the flux at exact t equal to 2 pm. This is the position of the flux. Xi s position is here at exact t equal to 2 pm. Right? If you select V2, what will happen? If you select V2 voltage vector through voltage source inverter, if you apply V2 vector across motor terminal, what will happen? Anyone? Don't get confused. Where is the position of V2? This is the position of V2. If in next sample, next instant, at exact t equal to, before t equal to 2 am, this is the length of, at exact t equal to 2 pm, if you apply V2 vector, what will happen? This one, V2 is nothing but what? V2. This V2. If you are adding some voltage, if you add some voltage in a particular time, what will happen? Flux will also add. This is nothing but, this is the amount of extra flux. Delta Is will add. So actual flux plus extra flux, what you will get? Your resultant flux, your actual flux length is increases. At the same time, what about angle? Angle is also increasing. Now you can tell what will happen here. What is happening? See, if flux error is positive, torque error is also positive, your job is, you don't have any option, you need to select V2. If you select V2, flux will increases, torque is also increases. But in next case, my requirement is, I want to increase the flux, but I want to decrease the torque. That is my requirement. If you want to increase the flux and decrease the torque, what is the voltage vector is mainly responsible to satisfy your requirement? Anyone? So aim is, next instant I want to increase the flux length, vector length I want to increase, but delta I have to decrease. Flux vector I have to increase. My aim is flux I need to increase, but torque I need to decrease. V1, no, if you take V1, what will happen? Change in load angle is very less. Instead of V1, if you select V6, what will happen? If you select V6, flux is increases, change in delta is also more. Compared to V1, if you select V6, change in delta is more. Change in torque, decreasing in the torque is more. Understood? Clear? This one, give me 1 minute. I will try to explain using different phasor diagrams so that you will understand this concept. Yeah. See here, this is about phasor diagram. This is about phasor diagram of the three-phase induction motor by adopting DTC method. It is a very simple concept. It doesn't require any three-phase to two-phase transformation or three-phase to two-phase. No Clark, no Park, right? One more important thing is here it is not an indirect control. This is a direct torque control and direct flux control method. See here, let us assume that this is the actual position of the flux, right? At t equal to 2 pm. If you want to increase the flux and also if you want to increase the torque, if you select V2, what will happen? This vector, this actual flux vector length will increases. Actual flux and additional flux. This is the red one is the resultant actual flux. So actual flux length will increases. Next at the same time delta will change to delta plus delta. So angle is also increases. So finally using V2 we can satisfy these two conditions. Similarly in case 2 requirement is I want to increase the flux, I want to decrease the flux. So decreasing the torque. If you want to increase the flux and decreasing the torque, by selecting only one voltage vector we can satisfy these two conditions. See, in case of electrical drive, control objectives are always flux and torque. Your job is you need to control these two parameters. You need to target only two variables, flux and torque. See, by selecting V6, what will happen? This is the initial position, right? By selecting V6, we can increase the length and also we can decrease the angle between the stator flux and rotor flux. If angle is decreases, torque will decreases. Now this is the last condition. Here, what is the condition here? What is the requirement? Customer requirement? Flux need to decrease, torque you need to increase. This is the initial position, right? So, if requirement is this one, if requirement is increasing the torque and decrease the flux, immediately you have to select V3. If you select V3, what will happen? This length will decreases. And also this angle will, this is the initial angle, this is the change in angle. Angle is also increases. This is a very beautiful concept. Here in DTC, by using simple switching states of the voltage source inverter, simply they will regulate the magnitude of the stator flux and they will regulate the position of the flux. By changing the magnitude and position, by changing the position, we can control the torque. By changing the magnitude, we can control the, we can satisfy the flux loop. Flux loop we can satisfy, torque loop also we can satisfy only by choosing proper voltage vector. So finally this is about logic behind direct torque control method. This is called switching table, voltage switching table of the direct torque control method. Only this is called predefined table. See, based on the stator flux position where it is there, if it is in 0 to 60 degrees or 60 to 120 degrees, right? 120 to 180 degrees, 180 to 240, 240 to 3, right? 300, 300 to, based on the position of the flux, you have to select proper voltage vector. By choosing proper voltage vector, we can control flux and torque directly without any orientation, without any control. This is a very beautiful concept, very advanced method, right? See, most of the EV application in industrial drives application, even in Vijayawada steel plant, already I told, in Vijayawada steel plant, to control the drives speed effectively, they are adopting DTC only, right? Shall I stop here? What is time? 3:30. Okay. If anyone having doubts, you can ask. I will give 5 minutes time to discuss. By 3:30, I will wind up the session. If anyone having doubts, you can ask. Otherwise, I will ask some questions, 2 or 3 questions I will ask. Fundamentals only. I will not ask any questions related to whatever I am teaching today. I will not ask. I will ask only fundamental questions. I don't know how many students are following or not. I don't know whether this session is effective or not. I don't know. I thought participants are faculty or research scholars, like that I thought, but many percentage of the students are more. Undergraduate students are more. It is very difficult to explain the concept in detail, advanced concept. Anyone having doubt, you can ask. What is bandwidth? I will ask questions. If you are not asking anything, I will ask questions. What is bandwidth? You heard name about bandwidth? What is bandwidth? Bandwidth will decide the accelerating rate. Please start to understand. If bandwidth is more, tracking to its reference is good. Your actual signal, it will track its reference very fast if bandwidth is very good. If bandwidth is very poor, here bandwidth is less, nothing but system is lazy. Bandwidth is good, nothing but system is very fast. Right? Now my question is, who will decide the bandwidth of the system? Who will decide? Your system poles will decide. If you take any system, it is having its own characteristic equation. Am I correct or not? Any system, if you take any system, it is having its own characteristic equation. Based on the characteristic equation, we can decide what is the position of the poles. You know poles, you heard poles, zeros in control system, right? Poles, zeros. What is the significance of poles? If there is any pole is there closely to origin, what is the issue? It is called dominant pole. You know, you heard about dominant pole? Okay, leave it. Leave it. I want to ask one important question. Already you have studied control system. Last question. What is the main object of control system? Subject. Why we need to study control system? What is the object of control mechanism? By using control system, by using control logic, we can able to reject the disturbance. That is the primary object of the control system. If there is any disturbance, what will happen? Your system will deviate away from the reference. Right? By using closed loop mechanism, we can able to reject the disturbance. And also we can track the reference. That is the primary object of the control system. And also we can improve the dynamic response. Dynamic response we can improve, bandwidth of the system we can improve by using closed loop. If student is working independently, bandwidth automatically by nature it is poor. If student is working in faculty loop, bandwidth it will improve. If system is under control, automatically dynamic response will improve. Please try to understand. My suggestion is particularly electrical student, all subject, whatever topics are there for electrical engineering, for all topics there is a mathematical proof is there. If you take other subject, you don't have any mathematical proof. Please try to understand. Your job is, my request is, here before learning the concept, first you need to extract what is the equation related to particular topic you need to extract. So that equation, in that equation, what are the independent variables, what are the dependent variables you need to identify. If number of dependent variables are more, control is difficult. So what are the control methods they are using to minimize the complexity? That you need to understand. For all concepts, there is a mathematical proof is there. If it depends on mathematics, subject become easy. You no need to by heart anything. You no need to spend more time also, right? Okay. If you anyone want to ask questions, you can ask. Otherwise, I will wind up session. Shall I stop here? Thank you. No.